Yeah, so now let us understand the DC channel gain in the optical wireless DC channel gain, which is defined as HIJK, where I is the LED index. In our case, there are two LEDs, so I will have value 1 and 2. J is the PD index, photodiode index. Again, there are two photodiodes with each receiver, so it will have value 1 and 2. And K is the user index. So HIJK is a DC channel gain between LED I and photodiode J for the user K. And it's a 2x2 matrix for each user. And this is given by earlier classes. We have discussed this, where M is the Lambertian order. It basically defines the radiation pattern of the LED, Lambertian order. And this is the area of the photodiode. And D is the distance between the ith LED and the jth receiver. So this is the distance. And this mu is filter gain. You might be using some filter at the transmitter. And this is the concentrator gain, which is used at the receiver. And phi is the emission angle. And theta is the angle which the PD makes with the normal. So this is P photodiode angle. Let me illustrate this. So this is your transmitter. This is, say, for your receiver, and this is the LOS path. So this angle which the transmitter makes, the LOS path makes with the normal, is phi, and the angle with the normal makes with the LOS path is theta. And this is the FOV of the angle. This whole thing is the FOV of the angle, FOV of the device, of the photodiode. So HIJK, that is a DC channel gain, is given by this expression. Now, remember when we were discussing about MIMO, we discussed about two types of receiver. One was zero forcing receiver, and the other was MMSC. So this is zero forcing, and this is minimum mean square error. So in this analysis, we will use zero forcing because of simplicity. So in zero forcing receiver, if you recall, the Y, the estimated X, which I am calling is X hat, is given by zero forcing function into Y. Y is the receiver. And if you recall, FZF was defined as CDO inverse. So it was defined as this. So this is H minus 1 minus, this inverse will come here. It's defined as this. So this becomes H inverse, H conjugate minus 1 into S conjugate, which then this is 1. So basically it gives you H inverse, or is equal to 1 by H. So this is the function which you have to use on Y, so that you can get estimated output. So this is possible because we are using 2x2 MIMO, and the inverse exists because there are two LEDs and two photodiodes. So FZF is defined as 1 by H. So if I write my receipt power is y, this is responsivity into receipt power p opt into modulation index into say channel matrix into x plus n. Now I know hx into n, and the estimated value is fz, f 0 forcing on in y. So this will give me, I'll put the value of y here. So this, put the value of y, and also fz is equal to 1 by h. So this gives me responsivity into p opt into xi x plus n. So this will be n by h. So just to normalize it, I can divide by this. This is something constant. I can divide this by this factor. So what I get is x plus n over h. This will come at the bottom into gamma p opt index. So this is what I have written here. So this anticipated for the kth user, or estimated for the kth user, is x plus 1 by gamma p opt xi into h inverse into nk. This is the noise, so this is nk. So this is a zero forcing receiver I have used here. Please refer to earlier classes for better understanding of zero forcing receiver. So what I need to do now, I need to find out the order of how I'm going to define the order for successive interference cancellation. So in this case, there are two DC channel gains which are involved. So I will be using the sum, and the sum which is the maximum, I'll place them in this order. So basically this will give this is, for example, this is a user index. This is the LED index. And this is the photodiode index, PD index. So basically I will see the DC channel gain on the user 1 coming from the LED I to both the receivers. Similarly, this is for the user 2, this is for the user K. So I will find out an order, and so this is a decreasing order which I have fixed. So this becomes my order of successive interference calculation. All right. So basically, where I have the more channel gain, that will be decoded first, so on and so forth. So this is the order. And how do I allocate the power to the LEDs? Because in NOMA, allocation of the power is important. So there are two methods which are used for allocating power. One is called as gain ratio power allocation, or GRPA, so this is the electrical power allocated to the kth user from the ith LED. This we had defined earlier. So electrical power allocated to kth user by ith LED, or from ith LED. And this is to the k plus 1th user, to the I. And the ratio is actually, this is with respect to the first user. So you will find H1I1 plus H2I1. So this is for the user 1. So this is with respect to user 1. And here you have H1I for the k plus 1th user, and similarly H2I for the k plus 1th user. So you take the ratio with respect to the user 1. So that ratio and raise to the power k plus 1 in order to ensure fairness. This is to ensure fairness. So if you allocate in this way, power allocation to different users from the different LEDs, which I am calling as GRPA. So this is method say 1. The other method could be I take the difference of power allocation and normalize it. So this is, as earlier, electrical power allocated to the kth user by the ith LED. This is to the k plus 1th user by the ith LED. And here I have taken the difference. So you see this H1I1 and subtracted with this, and similarly this and this they are subtracted, and this is with respect to the first user, sum of the DC channel gain of coming from the ith LED to different photodetectors, to two different photodetectors as 1 and 2 and raised to power k. So this could be, one is based on sum addition, the other is based on gain difference. So using these two methods, that is GRPA and GDPA, there can be other possibilities of power allocation. But if I take this kind of power allocation, then what I get is this kind of curve. So let us try to understand this. So this is a achievable sum rate versus normalized offset using OFDMA and NOMA. So this is R by R. So when this value is 1, that means that user is at the last location. Remember we had this as the system model, LED 2, 1, and we had user 1 here. This is a user 2. This is user K. So with respect to this distance was R, small r, and this has footprint say up to this point or say this point, and so this distance, maximum distance, will be capital R. So when R divided by R is equal to 1, that means the user is at the extreme end. So this is what it shows. So basically it tells you the sum rate at different points in the room. So if I have only 2 users, for example, and so OFDM, this is normal OFDM, this is not NOMA. So this is shown by this. So this is the OMA for k is equal to 2. So this is what you get, the sum rate. And if you use 2 types of power allocation method, that is GRPA and normalized GDPA, one is the addition of the channel gains, other is the difference of channel gains for k is equal to 2. So these are the respective curves you will get. So with NOMA is this is NOMA using algorithm GRPA. This is again k is equal to 2. And the third one is this dashed line. This is NOMA. You are using the difference algorithm, normalized gain difference algorithm, DPA, and this is k is equal to 2. So this performs slightly better than the GRPA algorithm and definitely better than the normally OMA is equal to k is equal to 2. So same trend is there for k is equal to 3 when the users are 3. So you have the same pattern. So what we see here in NOMA using NGDPA is a power allocation strategy, we get the maximum sum rate possible inside the room. So this we have analyzed MIMO NOMA system using VLC, and this is much better as compared to OMA, so which will meet some of the requirements of 5G and Internet of Things. There are further analysis which one can do, because if you see the NOMA VLC assumes, one analysis which you can do is using perfect channel state information. This is channel state, because you require channel state for successive, because you have to find out the order. So you have to correctly measure the channel state information or DC channel gain. Channel state information. So one can do analysis with perfect CSI, but in practically it is never the estimation of the channel is never perfect. There are imperfections, there are errors. So one should do analysis with imperfect CSI, and this could be because you are, for channel estimation, you are sending some pilot signals, and that can be in the form of RF or IR. So this may introduce some sort of impairment, or the users may be moving, the channel CSI will change or DC channel will change. And when you are finding out the channel, you are doing some analog to digital or digital to analog conversion. So there will be some sort of quantization error. So these are the things which will make your channel estimation not very accurate. So while doing the analysis, one should consider these effects, which is what I mean by NOMA VLC with imperfect CSI. Another issue could be, the CSI could be noisy. The estimated DC channel gain for K user, for example, will be some HK, which is the actual value, plus some channel estimation error. This is, say, channel, because there may be some noise present, and this will result into some estimated value which is different from the actual value. So this is channel estimation error. And so this has a normal distribution with zero mean and some variance. So when I estimate HK, so this will be something like this. The distribution will be HK into some variance. So this becomes, under noisy conditions, the estimated value will be something like this. So this also one should take into account while doing the, defining the ordering or calculating the channel gain. There can be an issue with outdated CSI. Suppose the user is moving very fast, and whatever information you have got for the channel, it is no longer valid because the user has moved to a different location, or there is some sort of shadowing effect has happened. So sometimes you will get a CSI or channel state information which is outdated, which is not current. So this should also be taken into account, and this basically comes from the fact that shadowing effect or user moving fast. The other issue would be VNOMA VLC with dimming control. So variable NOMA VLC with dimming control. Now, as we have seen earlier, when you are using optical wireless communication or visible light communication inside the room, you should be able to see the performance, or you should be able to maintain the performance under dimming condition also. So the system should work in dimming condition also. So when you dim the light, basically you are reducing the power. So one has to, while doing NOMA, specifically when you're doing power domain NOMA, this becomes very important. The dimming becomes very important. So this is another area where still a lot of work is to be done, where you are able to use NOMA under dimming conditions. So this is another challenging area. So these are some of the few challenging areas which are still being worked on, and so to get the correct estimation, one has to consider all these impairments. So we'll stop the discussion of NOMA in VLC now, and we will now take some other applications of optical wireless communication system. And the next application which we intend to take is coexistence of Li-Fi and Wi-Fi. And then we will also have one application which is vehicular to vehicular communication. So these are the two things which we'll cover as part of the application, and these things are also covered as a simulation exercise towards the end of the course, wherein there are 5 simulation exercises, basically dealing with indoor communication, dealing with different modulation, for example OFDM, and Li-Fi, Wi-Fi coexistence application, and underwater simulation or simulation exercise, and also typical vehicular to vehicular communication using visible light. So these are the few simulation exercises which will take up after we have discussed the theory part of it. Thank you.